plus 8 cosine of 0.75 pi n, right?
Yep.
All right, good. Now, this wasn't where I intended to start, but this is a good example for it. Y of n turned out to be 1.5 plus 4 times 0.148.
8.
48
No,
cos
183. 0.183.
183. Okay, cosine 0.1 pi n minus 2.05.
Yep.
0.05 plus 8 times 0.0026 cosine 0.75 pi n minus 1.9.
I'll admit I'm impressed.
It just all of a sudden, yeah, just, I'm in the zone. Well, I want to go on with the same example because there's something here that's very fundamental. And the 1.5 is a DC term, and that has nothing to do with what I'm going to talk about. But I'm going to write this 0.18 times 4, 0.72 cosine of 0.1 pi, and now I'm going to factor that out. 2.05 over 0.1 pi. And I've still got MATLAB up here for this one. 2.05 divided by 0.11 times pi. And that is 6.53. N minus 6.53. Okay, plus 0.0 26 times 8, 4. I could remember the numbers, but I can't do the calculations. If that's 0.25 multiply 8, that's 0.04, I believe. Cosine of 0.75 pi n minus 1.9 over 0.75 pi. 1.9 divided by 0.75 times pi. And that one's 0.881 approximately. Okay. 0.81. Okay, there we go. I want you to look at this. Now, all I'm doing, we had done all the hard calculations last time, right? And when I point to something, I want you to tell me what you would call it. That 2.05, what would you call that? It's cosine of 0.1 pi n minus 2.05. What is that called? Magnitude, frequency, phase. Okay, so this here and here, those are called phase shifts. Where did they come from? You remember we calculated the gain at each of those frequencies, and I split the gain, I put the gain in polar form, and the magnitude went here and here, and the phase term went there and there. You remember that? All right. I calculated gain at each one of those frequencies by plugging in z equals e to the j 0.1 pi, and z is e to the j 0.75 pi, and I did that polyval command to calculate those. Okay, and those were the phase terms at those two frequencies. That's what we did last time. What did I just do right now? I did some kind of a manipulation, and I converted those phase shifts into, what's that called? N minus something? N is our time variable. Time delays. Okay, so I converted those two into there time shifts. So what does that mean? And by the way, how did I get that? What I did was write cosine of 0.1 pi times n minus 2.05 over 0.1 pi. And then cosine of 0.75 pi times n minus 1.9 over 0.75 pi. You see that? And the numbers there, I just used MATLAB to calculate those for me. Okay, so does this look like a time shift there? Now, I don't want you to be worried about n minus 6.53, the fact that it is not an integer, or n minus 0.81. That turns out to not be a big deal. If you want to know more about it, talk to me outside class and I'll explain it. But is n minus something a time shift? Okay, yeah, so what this tells you is a phase term is just a time shift. That's all it is. Okay? And in a way, you kind of knew that, because if I had a cosine function like that, here's a phase term. If I've got a phase that goes with it, that's no longer a pure cosine, is it? Why? Because I have shifted that over in phase. But that's just a time, this is a function of time. That's just a time shift. Right? Y'all agree with me? Okay, now, what does it all mean? Here's what it means, and this is why the phase response is important. Look at this. This term, this particular sinusoid, it got shifted by 6.5 samples. What about this one? It got shifted by less than 1 sample. That's a problem. Okay, so here the different frequency components are shifted by different amounts, and I mean in time, by different amounts as they pass through the system, pass through the system. And this is actually the definition of what we call phase distortion. And when I use the word distortion, that means bad, right? Okay? Phase distortion, when you distort the phase, it means you are delaying different things by different amounts. Let me show you in continuous time what this means with an example that you've all surely seen at one point or another. You remember when we have talked about, let's say, a periodic square wave like this. What I'm drawing is a square wave with a duty cycle of a half, positive half the time, negative half the time, and a DC value of 0. Do you remember talking about Fourier series for that? The Fourier series coefficients are a sinc function. You remember that? Yeah. Okay. And so here's what you do. And to build that up, you start with your fundamental frequency, which fundamental kind of looks like that already, right? Now I'm taking you way back there. This is not something you've seen recently. This is like from 202. And then you take the second harmonic is missing. The third harmonic looks like this. Yeah. Remember seeing a picture like this? Okay? And as you add more harmonics, you get something like this. Let's see, I'll add the 5th harmonic. Now let's add like to the 10th or 11th harmonic. And you get something that does like that. Okay? Right? And they add up. The harmonics add up in a certain way. You've got to have exactly the right coefficients out front, but you also have to have the right phase relationship. If you miss the phase relationship, notice here's the 1st harmonic, here's the 1st and 3rd harmonic. If you miss the phase relationship up, you'll wind up with something like this. You'll get a signal like that. Okay? They didn't add up the way they're supposed to. The harmonics have to add up with a very certain phase relationship. Notice so it pulls it down there, and it's symmetric, about 0, it's even, and all that. And you wind up with a signal like this. Okay? If you distort the phase, it's got the same harmonics in it. The harmonics have the same energy, each one of them. But instead of adding up a sine wave like that, I added up, I shifted the phase on it, and it became a sine wave like that. Right? Peaks and valleys are not in the same location. So, the point is, that's what's happened here. I delayed one frequency component by this, and I delayed the other one by something else. If they get delayed by different amounts, it's what's called phase distortion. Okay? Now, I'm going to come back to that maybe next week, but I'm just introducing it. I want you to know what it means now. And that particular example shows it. This phase delay turns into a time delay, and if that time, now the phase is not the issue, it's the time delay should be the same for all of them if it's going to have no phase distortion.
So that one doesn't.
Huh?
That one there, the live end does not.
This one?
Yeah.
Yes.
It obviously doesn't. So it's going to look like that.
This one has phase distortion?
Right.
Yes, it does.
That's
Okay,
the
yes.
there,
Right.
and you don't want that.
You don't want that generally.
So the first, the top equation with the phase shift, we don't really, it's okay.
Yeah, what you get there, those don't have to be equal. Those should not be equal, actually. But when you factor this out so that you get a time delay, n minus, you want all those time delays to be equal or very close to equal. And if they're not, that's when you have phase distortion.
So you mean equal to which
Whatever, if this one turns out to be like n minus 3.5, this one should turn out to be n minus 3.5.
Okay, I see.
You want them to have the same number of time delays. Okay. So, yes, you would like that. If you have that, if all your frequency components have the same amount of time delay, then you don't have any phase distortion, and that's a good thing. But it's not quite that simple. Okay, there's more to it. We're going to deal more of it next week. I just threw this in here because we had worked that problem, and I wanted to put it in terms of time delays and mention that. And we'll get back to it in another couple of lectures. Okay? Good? All right, so enough on that problem. Let's go on with this frequency response idea. And you remember talking last week or Monday, whenever it was, about distances to poles and zeros and all that as you go around the unit circle. We said h of e to the j omega is h of z evaluated at z is e to the j omega. This is on the unit circle. Right, you're going to go around the unit circle. And we said that this could be written as a constant out front times the product of distances to zeros over the product of distances to poles, which explains why, as you go around the unit circle like that, when you get close to a pole, the response will go up, and when you get close to a zero, the response will go down, which is another way of saying what I have drawn there is a, what kind of filter? Pole over here and zero over there. The response at DC is going to be right there, 0, and it's going to do something and then go up. So pi is right there. What is that? High pass? Yeah, that's a high pass filter. Now, I want to do something a little different. Let's say, for example, that I have a system. A system has a pole, just a single pole, at z equals a, and a 0 at z is 1 over a. Okay? Just one pole, 1 0. Now, I want to assume, but I really don't have to, it just makes the math a lot more straightforward. Assume A is real. Okay. A is a real number. And if this system has a pole at A, now you might say, boy, I hope that pole is inside the unit circle. And I do too. So let's say it's there. There's a pole at A. Where is the 0? Can you tell me? 1 over A, of course, but what does that mean? If A is there, where is 1 over A?
It's outside the unit circle.
Is it guaranteed? Yeah, sure.
It's less than 1.
That's right, because A is less than 1, 1 over A is guaranteed to be bigger than 1, right? Okay, so it has a 0 out here, and for now, there's a 0 at 1 over A. For now, we don't worry about zeros, do we? Because the poles determine stability and causality. So my transfer function would be z minus 1 over A over z minus A. And there could be a constant out there, couldn't there? If I put a constant out front, I can tell you about a constant. But does it still have the 0 on pole that I said? Yeah, it does. And so that constant can be there. Or I could just let the constant be 1. So I may throw it out. The constant could be there or it might not be there. Either way, I've got a pole at A and a 0 at 1 over A. Agreed? All right. So I'm going to talk about the frequency response. And before I start, I warn you it's going to be several steps of algebra to get to where I want. H of e to the j omega is e to the j omega minus 1 over a over e to the j omega minus a. Right? Is that what frequency response means? Plug in e to the j omega for z. Okay. What about gain? We've been talking about gain primarily, so I'm going to take absolute value of that. Or I should say absolute value, magnitude, because it's a complex expression. Okay, on the right-hand side, e to the j omega can be written as cosine omega plus j sine omega minus 1 over a. And in the denominator, that is cosine omega plus j sine omega minus a. And then I want to take the magnitude of that. There's a few steps here before anything. You'll look at it and say, this is just getting more and more complicated. And it will for a few steps. I want to take magnitude of that. How can I do that? Notice I've got numerator in rectangular form and denominator in rectangular form. How do you take magnitude? Real part squared plus imaginary part squared. Okay? So, and then take the square root. That'd be the square root of all this. Cosine omega minus 1 over a squared plus sine squared omega. Denominator would be cosine omega minus a squared plus sine squared omega. And as I said, it's going to look like it's getting more and more complicated, but all of a sudden, trust me, it's just going to simplify, and we're going to be left with a really interesting expression. So, expanding all that, what is that? Cosine squared omega minus 2 over a cosine omega plus 1 over a squared plus sine squared omega. Denominator looks very much like that. Cosine squared omega minus 2a cosine omega plus a squared plus sine squared. And when you look at that, you immediately say, oh, I see something really fun. What? Numerator and denominator both have a what? Terms. Haven't seen that yet, have you? Right, cosine squared. Right, cosine squared plus sine squared is 1. Right. So that part of it looks interesting, and the rest of it does not look so much fun. But, all right, that's going to give us square root. Cosine squared plus sine squared is 1 minus 2 over a cosine omega plus 1 over a squared. And the denominator is cosine squared plus sine squared is 1 minus 2a cosine omega plus a squared. Now, I can forgive you if you still don't see where it's going, but one more step and you will. You see those expressions, they look similar, numerator and denominator. They've got some similarity there. And here's what I'm going to do. I'm going to multiply this numerator by a squared. Can I do that? And a is just as I said, a real number. If I multiply that by a squared, I need to multiply by 1 over a out front. Would that be true? Okay? And when I do that, I get 1 over a, the square root. Tell me what the numerator is. I'll get you started. A squared, 2a cosine. Last term? 1. Denominator, 1 minus 2a cosine omega plus a squared. Okay, how do you like that? Do you like that? Why? What is it? What happens here? Look at that. 1. Am I right? Y'all see that? Okay. 1 over a. Okay. It's interesting. What does it all mean? Here's what it means. Let's see. Magnitude h of e to the j omega is 1 over a. What is 1 over a? A function? A constant? Animal? Vegetable? Constant. Okay, so it's just a constant. All the omegas dropped out. And so, if I were to plot the response, looks like this. This is versus omega, 1 over a. 1 over a is just a number. Oh, and by the way, if I don't like 1 over a, if I wanted that constant to just be 1, throw in a k in front of it that equals a. And a over a will give you 1. What do we have there? What kind of a filter? This is the kind of filter we don't talk about much. You've got low pass, you've got high pass, you've got band pass, you've got band stop. What is this? It's what's called all pass. Okay? In other words, what does it do? Whatever the amplitude of the input sinusoid is, comes out with the same amplitude. Why would we do something like that? There are a couple of reasons. One reason is if the gain response is just a constant, the gain's not doing anything. So what must we be working on? Phase, right? And so if you have some kind of a phase shaping filter, now why would you have a phase shaping filter? To remove phase distortion, for one thing. Okay? If you have a phase shaping filter, you would want the gain, you're wanting to massage the phase in some way. And by saying we want to change the phase, I'm implying, but not the amplitude. This won't change the amplitude. But there's a better way. There's a more important reason for doing this. If I were to say that I have a filter, and that filter, no, let me back up. Let me explain this graphically. All right, pole 0, A, 1 over A. Here's what it says. And this is not obvious, but this is actually what we just proved, believe it or not. As I go around here, we draw with a green marker. Remember Monday we were talking about calculating distances from the unit circle to the poles and to the zeros and dividing them? Okay? Here, and it doesn't seem like it, but this is what we literally just mathematically proved. That if I take the distance to the pole and the distance to the zero right there, and I divide them. Distance to zero divided by distance to pole, right? And then I go somewhere on around here, and I take distance to the pole, there, distance to the zero. And I divide distance to zero by distance to the pole. The answer will be a constant, no matter where I am around that unit circle. Okay, so over here, I take that distance, and I divide them, I'll get the same answer. Okay? Is that obvious? No, that's not probably not obvious, but we've gone about this problem kind of backwards. I said, yeah, we have already proved it. It's always 1 over A. That's what we just did. We did e to the j omega minus the 0 divided by e to the j omega minus the pole, and we did a little bit of algebra, and we came out with a constant. And that e to the j omega can go from 0 less than or equal to omega less than or equal to pi. Actually, less than 2 pi. We can go all the way around the circle. We proved it. Okay? So, let's see. That's all pass, which means I'm going to give you some transfer functions. H of z, and these are going to have actual numbers in them. Z minus 0.8 over z minus 0.5. I'll call that H1. H2 of z is z minus 1 over 0.8 over z minus 1 over 0.5. H3 of z, z minus 1 over 0.8 over z minus 0.5. H4 of z, I think 4 is as far as I can go. Z minus 0.8 over z minus 1 over 0.5. And now, I want you to picture that there could be a constant out in front of any of those, so I don't want to worry about the constant. Okay. Tell me about those. Notice I've got a 0 at either 0.8 or 1 over 0.8, and I've got a pole at 0.5 or 1 over 0.5, and yes, I know those two. I don't want you to worry about stability. I don't want you to worry about a constant factor out front. Those have, let's see, we're starting, the very first one has a 0 here and a pole there. That's kind of a high-pass filter, isn't it? Wouldn't you agree? You start out over here closer to the 0, and as you go around, you wind up closer to the pole. It's not a great filter of any kind, but it's kind of a high-pass filter. Okay, turns out every one of those will have that same response. Why? What did I just say? This Z minus A over Z minus 1 over A is all pass. So what does that mean? No, I had this backwards. Doesn't matter. 1 over A and Z minus A. If that one's all pass, then these will have the same response, every one of them. Why? Because how could I get from the very first one? I just realized the very first one, that what I'm saying is not obvious. Z minus 0.5. Got a certain response. What if I multiplied it by this? Z minus 0.8, Z minus 1 over 0.8. What property does this filter have? All pass. That one's all pass. So, and when I multiply them, those go out and I get Z minus 1 over 0.8 over Z minus 0.5. And I've got that one below it, right? What happens to the frequency responses when I multiply them? They get multiplied, right? So if I multiply a particular filter here by an all-pass filter, the all-pass doesn't affect the gain. So the gain response of that one and the gain response of that one will be the same. Okay? And to get those others, how would I do that? Just multiply by different all-pass filters. Okay? They will all have the same gain response. Now, there are two of them. These two right here, I'm not going to deal with. Why? Because, what? Because they are, yeah, what is? Poles. Right, those two are unstable, so I'm not going to mess with those. But all the others, whether the 0 is at 0.8 or 1 over 0.8, 1 over 0.8 is 1.25, I believe. Either one of those, back here, these two. 0 at 0.8, 0 at 1.25. They will have the same gain response. Why? Because to get from one to the other, all I have to do is multiply by an all-pass filter, which doesn't affect the gain response. Okay? So, if I were to say, I have a particular filter that I have discovered, and it has a transfer function like this, and it is a wonderful filter. Let's say Z minus 1, Z plus 1, denominator, I guess that'll work, denominator Z minus 2, Z minus 1.5, and Z plus 1.25. Okay. What if I were to say, now here's how you would use this. If I were to say that particular filter has exactly the gain response I've been looking for. Up until today, you would have said, well, buddy, you're out of luck. Why? I don't care if you want that gain response for that filter right there, because that filter is, what? What's the problem with it? You can say it.
Easy than bottom.
What's the problem with that filter? Look at that denominator.
Is it because it's a higher order?
No, you're making this much too hard. Look at the
Poles are outside
denominator.
in a circle.
Yeah, the poles are outside the unit circle. So until I have told you this, if somebody had showed you that and says that has exactly the gain response I want, you would have looked at it and said, tough luck. Poles outside the unit circle, that one's going to be unstable or non-causal. Right? What I have just told you in the last half an hour is this. It's your lucky day. I'm going to write another transfer function, z minus 1, z plus 1, and the denominator, z minus 0.5, z minus 2 over 3, and z minus 0.8. Okay? You like the gain response of the other one? This one's got exactly the same gain response. And it's stable. That's right. All the poles are inside the unit circle. So you can reflect. Now, I have done all this based on real poles. The math is a little bit messier, but it turns out it works exactly the same way for complex poles. Okay? I've been working with real poles and zeros. So, if I did this, what would that be? If I were to say, here is another filter with pole zero plot, pole, pole, pole there, and let's just say 0 there. Okay? Unstable, true? Okay? But it's got a frequency response that I really like. What can I do? I can redo it, a different filter, and this one will have the same gain response. I'm going to reflect that one in there by taking its reciprocal. And here's something I want you to appreciate, but it really doesn't matter in the end. When I take, let's see, that one's out there and that one's out there. When I take the reciprocal of those, they'll go inside the unit circle, won't they? But this one has a positive phase. That one will actually go down here. This one has a negative phase, and it will go up there. Okay?
Wow.
Sorry?
I see, that's a little bit wild.
Yeah, but in truth, it doesn't make any difference. Mathematically, that's correct, but in truth, it doesn't make any difference. Why? Because these always occur in complex conjugate pairs. You can just pretend that one went in there, which is on the same line, but magnitude's reciprocal, and you can pretend that one went in there. Because they occur in complex conjugate pairs, it doesn't make any difference.
But the one in the middle of the two, however, it has its positive, right? And then
Yes.
when you reciprocal is,
Yes.
you have to carry negative side, right, or no?
Right. But that's just like this, 2 and going into 1/2.
But isn't,
But
I think she's
it's
talking
the
about the negative sign on the.
Negative side, so is that have to
Oh.
be under?
Yeah, it'll keep the same sign. Or
It's the phase.
phase.
Or angle.
I'm asking, why is the z plus 1.25 and z minus 0.8?
Oh,
Yeah.
I apologize. No,
Yeah.
I'm sorry. I'm sorry. No, I just made a mistake there.
Alright.
Okay, I didn't see that error. Well, shouldn't have done that.
But I also have a question.
Okay.
So, since you said that we use the real code to plot in the
Right.
the Yeah.
Frequency response?
Frequency
Gain,
response.
okay.
But the thing is, you said that it's gonna be the same result of the
Yes.
imaginary number. The complex whole, right? The
Yes.
result is gonna be the same. So,
Right.
which is mean that you're gonna draw out the pack of the imaginary one?
Oh no.
The real,
I'm just saying, if you had something like that one at 2e to the j pi over 8, when you take the reciprocal of that, you would get 1/2 e to the negative j pi over 8. And that's what takes this one from up here down here.
okay.
But this one down here would be 1 over 2e to the negative j pi over 8, which is 1/2 e to the plus j pi over 8. So either way, so this one actually goes up there. But regardless, we could just pretend this one went in there because we got one at e to the minus j and e to the plus j. So that's why I was saying, to be mathematically correct, you have to do that. But because they appear in complex conjugate pairs, it doesn't make any difference. They'll still be in complex conjugate pairs. Okay? So now, we can deal, if you were to encounter a system with a pole outside the unit circle, and you don't want to mess with the gain response. So I keep saying that, gain response, gain response. What do you suppose does happen when you flip them inside? Do you suppose, these two are different functions, do we all agree on that? We just proved a few minutes ago that the gain response for those, take the h of e j omega and take the magnitude, is the same. Is everything the same? Turns out no. So what's different? If the gain response is the same, it must mean they have different. If the gain response is the same, they must have phase responses are different. Okay? Okay, phase responses will be different. But if you've got a system there and you want the same gain response, but you want it to be stable, and that's a good thing, you can use the second one, which means reflect all. What if, one last question on this, what if this one were at z plus 0.8? Could you reflect that one, and leave that one alone? And why would you? Because that one's already inside. Could you leave that one alone? Sure. Sure, just reflect the ones, whichever poles you don't like. Reflect them inside the unit circle, and the poles that are already inside the unit circle, leave them alone. Now, you may think I'm making a big deal out of nothing, but very soon, probably week after next, we're going to talk about phase relationships more, and we're going to talk about zeros. What do you know about zeros? Inside or outside the unit circle doesn't matter. Doesn't matter for stability, but it does matter for the phase response. Okay, and zeros inside the unit circle are better than zeros outside the unit circle, but it's not like poles. Poles outside the unit circle are totally intolerable. It's unstable. Zeros are better if they're inside the unit circle, but it's not absolutely critical. Okay? You have an exam to be working on, so I want you to be working on said exam. And let me, just so I can give you some hints, I have it here. Oh, notice that note on there says 432 students, but you can leave off one problem.